This is a video summary of our research paper to be published in MPJ Quantum Information. The title of our paper is Shortcut to Multipartite Entanglement Generation, a Graph Approach to Boson Subtractions. Hi, my name is Seung-Bum Shin, the first and a co-corresponding author of this work. The goal of this work is to provide a systematic and efficient method to generate probabilistic multipartite entanglement of identical particles in linear quantum systems. One of the promising approaches to this task is to exploit the indistinguishability of identical particles. In this setup, we generate multipartite entanglement with single particle sources, linear operators, and particle number resolving detectors. There are two possible categories of schemes available for probabilistic entanglement generation using identical particles: the post-selected and heralded schemes. The post-selected scheme prearranges which state to post-select and identifies desired outcomes after conducting operations. It is a widely used method for generating entanglement with relatively simple circuits. However, it is highly probabilistic and the successful operations can only be identified at the latest stage of the experiments. So it cannot be directly used as quantum gates in general. On the other hand, the heralded scheme employs single photon states in ancillary modes as heralds of the expected target states. It allows for sorting out the experimental runs for the target states without directly measuring them. Nevertheless, it requires several ancillary modes and particles to accomplish its goal. Consequently, designing circuits for this scheme is significantly more challenging, and installing the system is also more costly. So, especially in the heralding cases, it is crucial to establish the link between the target states and the structure of linear quantum networks. However, previous studies on the generation of multipartite entanglement have relied on the trial and error method for designing circuits, so it lacks a systematic strategy. In our work, we introduce a robust strategy to bridge this gap by utilizing a graph picture. Our graph picture is organized to describe the linear quantum networks, so we call it the graph picture of linear quantum networks, or simply LQG picture. This is the overview of our work. Heralded schemes consist of single boson sources, linear transformation operators, and heralding detectors. However, there has been no known reliable strategy to assemble these elements to generate suitable target states. To install our graph picture to overcome this problem, we need a simplified expression of heralded schemes that has a direct mapping dictionary to the LQG picture, and it is the sculpting protocol introduced in 2019. In this protocol, all the transformation elements and detectors are understood as boson subtraction operators, which were dubbed sculpting operators. And now the task of finding heralded schemes is replaced with the task of finding suitable sculpting operators for the target states. However, this picture itself still does not provide any systematic strategy to find schemes. And that's where the graph method comes into play. We map all the operator elements of sculpting operators to bipartite graphs so that each bipartite graph corresponds to a sculpting operator. Then, we can use well-established graph theoretical techniques to find suitable graph solutions for our target states. A brief explanation on the sculpting protocol is now in order. It consists of 3 steps: initial state preparation, operation with sculpting operators, which result in the final state. For the initial state, we prepare for a 2n boson state in n modes. Each boson has different states, either spatial or internal with each other. So as you see in this figure, each mode has 2 bosons and they have an orthogonal internal state with each other. Then we take a sculpting operator an to the initial state, and it subtracts n bosons so that each mode has only 1 boson after the operation. We need to set the amplitudes of the sculpting operator to extract 1 boson per mode. We call the condition no bunching restriction of sculpting operators. And such obtained final state can be fully separable, partially separable, or genuinely entangled. Then we analyze which type of entanglement is generated or not in the final state. We can also consider the QD generalization of the above protocol. It is directly achieved by increasing the initial boson number to d times n and subtract d minus n bosons. Now we map the elements of sculpting operators into graph elements. Well, actually, we can consider a more general dictionary of mapping the multi-boson systems into graphs, including creation operators. You can find the full dictionary in the supplementary information of the paper. It is a generalization of the graph picture introduced in this paper published in 2021. But for our current goal, it is enough to provide the correspondence relations of sculpting operators with bipartite graphs, because sculpting operators contain all relevant information in generating multipartite entanglement. As you see in this table, spatial modes correspond to labeled vertices in bipartite graphs, and Boson subtraction operators correspond to unlabeled vertices. They are unlabeled because they are identical with each other. And the spatial distributions of the Boson subtraction operator corresponds to the edges. And the probability amplitude and internal state correspond to complex edge weight alpha and psi. For the case of internal state, since we are working in some restricted computational basis, we replace the edge weight with some limited number of colors like red and blue. For the n equals 2 example, this is the most general form of sculpting operator, and it is mapped into this bipartite graph in our mapping. 2 circles correspond to 2 spatial modes, and 2 dots correspond to two subtraction operators, A1 and A2. And these dots is the unlabeled vertices here. After mapping all the elements of sculpting operators to bipartite graphs, we find two handy properties of such sculpting bigraphs for finding entanglement generating operators. First, no bunching restriction is translated as the first property. For sculpting bigraph of a sculpting operator AM, the probability amplitude weights are restricted so that only the perfect matchings contribute to the final state. So actually, it is pretty tricky to satisfy this condition for some arbitrary subtraction operator. So this is usually the main cause of the technical difficulties to find the suitable subtraction operator for the generation of multipartite entanglement. We can understand the meaning of this property intuitively with the n equals 2 example again. Now we set the amplitudes of the n equals 2 sculpting operator so that it satisfies the no bunching restriction. Then the graph representation of the sculpting operator is given in this form. We just omitted the probability amplitude weights because they are just equal to each other. And this bipartite graph is expanded to these four subgraphs. And we can directly check that these two terms vanish, and the final state is a summation of the perfect matchings, which becomes a Bell state. As I have mentioned, it is pretty tricky to find sculpting bigraphs to satisfy the no bunching restriction. But there is a special group of bipartite graphs that always satisfy the no bunching restriction. We dub them effective perfect matching bigraph, or simply EPM bigraphs. An EPM bigraph is a bigraph whose edges always attach to the circles as one of the following forms. And the nice property of the EPM bigraphs is stated as property 2, which is, if a sculpting operator is represented as an EPM bigraph, then the final state is always fully determined by the perfect matchings of the bigraph. The converse is not true. So it means that all the EPM bigraphs satisfy the no bunching restriction, but there are also some bigraphs which are not EPM bigraphs, but satisfy the no bunching restriction. And the combination of the properties 1 and 2 provides an extremely convenient insight to search for the suitable sculpting bigraphs, which is, if a bigraph is an EPM bigraph, and it is mapped to a strongly connected unipartite directed graph whose vertices all have different colors of incoming edges, then we can impose suitable edge weights so that the corresponding sculpting operator generates multipartite genuine entanglement. The second condition was first proved for post-selected schemes in this paper, but it can also be applied to the Boson subtraction schemes. Based on this strategy, we have found several sculpting bigraphs that generate essential multipartite entangled states. The simplest but very interesting graph solution is the GHZ generating bipartite graph. And you see that this graph has two perfect matchings, and also this is the simplest form of EPM bigraph. So we directly know that the final state consists of these two subgraphs, and we can also check that by directly mapping this graph into operators and check the final state. And indeed, the final state becomes the GHZ state. We also have found other solutions for the other types of entanglements like qubit W state with one ancillary mode and the superposition of n equals 3 GHZ and W state with 3 ancillary modes. And we can also increase the dimension of the internal states, which corresponds to QD entanglement. And this is the graph solution for QD-GHZ state. This bigraph has a very interesting structure because it is nothing but two copies of QB-GHZ state, and this one directly generates Q3-GHZ state. But by repeatedly piling up the same bigraph, we can generate the GHZ state of any dimension. I think this demonstrates the power of our graph method to find entanglement generating schemes in a very simple and intuitive way. Also, one thing I need to clarify is that we have also found the translation rules from these graph elements to linear optical circuits. So, once we find this sculpting bigraph for a target state, then we can directly draw a linear optical circuit based on the bigraph. So far, I have explained how the LQG picture provides a systematic strategy to find sculpting operators that generate multipartite entangled states. And this paper was uploaded about 1.5 years ago, actually, so I have written several follow-up papers related to this graph approach. For example, we can find more schemes for the other types of entanglement, like, the results in this follow paper. And also, as I've mentioned 1 page ago, we have provided type translation rules from the sculpting bigraph elements to linear optical circuits in this follow-up paper. In addition, the main focus of our current work here is the qubit entanglement generation, well, actually, except for the QD-GHZ case. But this follow-up paper uses the graph method to find heralded schemes for generating n-partite n-level totally symmetric and antisymmetric states. And they are interesting examples of QD multipartite entangled states. We believe that our graph method still has a lot of room to develop, and we expect it to serve as a promising tool in generating diverse heralded entanglement. Thank you for your attention so far, and whoever has comments or questions on this work, please do not hesitate to send an email to this address.